Thanks, Brad. Hello and welcome everyone to this presentation. Good morning. I am Vaibhav. I'm a recent master's graduate at Arizona State University. Today I'm going to talk about a research AIM-SDN, which is wherein we'll see how we can exploit some fundamental design flaws which are inherent part of SDN controllers and also stem from something that we call here semantic gap. So a little bit about history and also how do we see traditional networks. We know basic network, it consists of switches and it also consists of hosts. And more often than not, the switches are connected in some sense of topology, mesh, ring, or whatever it may. Here's the interesting part where the traditional network, in the traditional network, we store this routing information and also the decision to route the traffic inside the switch itself. Also, that is the case at every single switch or the router. However, when we introduce SDN, we introduce another level of abstraction. We introduce another entity which we call SDN controller. And we move all the storage, which was configuration storage, as well as the intelligence to route this network traffic to another remote place, again, which we call SDN controller. SDN controller at this point of time has centralized view of the entire network. So this is different from the traditional network setting where switches have only localized view and knowledge about what's happening in the closed box. Not so much in SDN. We have centralized view of the entire network. So what SDN essentially does and what we call in SDN setting is programming the network. It sends the installed configurations to the individual switches, routers, and then switches and routers can take forwarding decisions based on the configuration installed from SDN controller. So when I say configuration installed from SDN controller, someone has to put it. It can be applications. Now we are talking about software-based networking realm. We are into software world, so we are having software-based load balancers. We are having software-based firewalls. Also, network admins or any users for that matter. They install this configuration inside SDN controller, and based on the standard definition of SDN, we call this plane a logical abstraction where applications and users are sitting as application plane. The controller is situated in another logical abstraction, which we call in SDN setting as control plane. Finally, we have network, which consists of switches, routers, links, hosts. That goes as part of forwarding plane. Interesting stuff. And the reason for giving you this sense of SDN explanation is that there is a lot of flow of information that's happening from application plane down to control plane and so on and so forth to network finally, and vice versa. So this information flow that happens between these three different layers poses a lot of challenges. So when SDNs were not actually deployed in an enterprise setting, we did not have a challenge of storing a lot of information because it was still proof of concept. But now, as we speak in data centers, when we have SDN controllers actively in enterprise setting, we have a lot of information. So a couple of challenges that these SDN controllers are facing is how do you create a clear distinction of what information goes where? If you as an application or user install something in the network, what's the guarantee that information has gone successfully into the network? How do you ensure that? How do you, the third question can be, how do you create a clear distinction between state, what gets installed in the network versus the state that user or application had actually wanted to be of the network? So to solve that solution, there were many several approaches, but many industry players, vendors, came together and proposed a solution which is being defined by RFC 8342. That's a standard document which defines it is a document defining a network management data store architecture design. So as part of NMDA, when we see how does NMDA actually fits into the entire SDN structure, again, we have the same application layer. Let's just assume this cylindrical box is the controller. We have our network. So I had earlier said there's a lot of information going from application to network and vice versa. The applications use user-side APIs, which can be REST and REST APIs or whatever. This information ultimately goes into the data store. The cylindrical boxes that you here see is what NMDA has proposed. So this is where the clear distinction of information has happened now. For example, let's take an example. A flow rule or a modification of the rule that a load balancer or a firewall application wants to go into the network first goes into a configuration data store. It gets stored into a configuration data store because it's a required and expected configuration. Ultimately, controller has different services which take this configuration, puts this configuration of, like we say in SDN setting, programs this configuration into the network. However, now when load balancer has to work on quality of service kind of use cases, we take the information, for example, flow or node statistics, move the flow and node statistics from network, not to the same configuration data store, because then when we are mixing up and jumbling up the information at one place, we are having a better organization defined by NMDA. So this finally information, the information stored inside operational data store depicts the active state of the network, finally goes into applications, interested applications, so that they can take intelligent decisions of, for example, load balancing. So it is interesting to now observe these three different distinct layers in terms of different semantics and rules governed by this different layer. For example, applications, load balancer, firewall, or anything, has their own semantics. They have different governing bodies. They have different trust boundaries. Controller is, SDN controllers are developed differently by different organizations, again, different semantics. Network, finally, we all know, has different protocols, for example, BGP, netconf, OpenFlow in SDN setting, again, different semantics. So I'm talking about different semantics at different levels. So what is interesting over here is when the information flows between this semantic layers, there is a sense of misunderstanding of how this information should flow from top to bottom and vice versa. We'll see what it is in a bit. Let's just take another deep dive into NMDA. So now, since I've explained to you what semantic, I have provided a clear distinction of different layers in SDN in terms of semantic layers. So let's there you have application semantics, controller semantics, and network semantics. So so the rectangular boxes that you see over there are the data stores defined by NMDA model. We have candidate and startup data store, which are application. They put information into controller, goes into configuration. The loop that you see over there is 2 to 5. It goes from configuration to network, back to from network to operational, and again back to application. This loop is in a dynamically scaling network, or even in a data center kind of massive network, takes time. So this time lapse, right, of the flow of information from the top to the bottom and vice versa for network entities to take intelligent decisions. And like someone pointed out yesterday, that as in an SDN setting, everything is event driven. Because of this time lapse, we are seeing state inconsistencies. So what I want to gather your interest is, because of the semantic differences at different levels, there is a time lapse, and ultimately we see state inconsistencies. Another reason, like I had earlier pointed, different vendors are involved at different levels. But when I say different vendors, what I want to say is there are different trust boundaries. There are different trust boundaries between application controller and controller to a network, and vice versa. So because of this different trust level, there is no guarantee that the information going from top to bottom is being taken into consideration or care the way an application like load balancer or a security application like firewall had wanted it to be. So let's get into some literal details of what RFC proposes. So like I said, NMDA is a standards document. It clearly mentions that it admits, I should say, that the two different data stores in a setting, let's say just configuration and operational data store, can have different information. Fair enough. Easy example that we can imagine is an application is wanting to install a particular configuration into network, and the switch has died. If a switch has died, there is no way a switch can have that configuration in it. And of course, what is operational data store is having is the active state of the network. It will not have the same configuration for the particular switch. These two data stores can have different information. That's very true. We accept it. However, as part of the same RFC, the security consideration section claims that they have admitted that semantic differences have brought some inconsistencies in the information, or mismatch in the information stored inside data stores. However, it does not have any security impact on internet. Well, not so true. So in this research, we are going to invalidate the claims like this. And what we are identifying now from this different semantic levels is the semantic gap. The gap in understanding how things operate right from the beginning towards the end. When I say beginning, I'm talking about application. When I say end, I'm talking about the network and back. So there are different kinds of data information which flows right from the beginning. It gets converted to some sense for the protocol abstractions in the SDN from applications to controller, and then controllers services convert this information, for example, into open flow rules to get installed inside open flow based switches. So again, conversion of information there. So there, the information keeps changing, but the intent should be same. However, it is not so same. There are different trust boundaries. We have already seen that. And of course, there are different vendors, which makes this problem all the more difficult. But we cannot make someone accountable for the entire setting. We have to run behind different vendors or the contributors at the 3 different semantic levels. And ultimately, this leads to severe security issues. No. So here in this presentation, we are going to see that how we are invalidating this claims that security is not impacted in this standard, which is incorporated by most of the SDN controllers in the market today. So let's take into example what a use case of challenge that a semantic gap proposes. For example, a user or application is wanting to install configuration into network. What it does is it takes the configuration, installs into a Datastore, or it is being consumed by an application. It's a basically producer-consumer problem. So as this information flows, I want you to notice the color of the flow rules over there. Blue depicts that who is the owner of this information. Now there is an orange colored service which takes this flow rule into consideration and puts it into another Datastore, because now in our typical SDN setting, information is flowing from application to network. Someone inside controller will take this information and in turn program the switch. Someone again, which is a service inside SDN controller, takes this information and stores it inside operational data store. So now if you notice the color of the flow rules, what we can clearly see is there is blurred responsibilities. There is mixed sense of understanding who owns this, who should be accountable for this. Why is this a problem? A clear example should be information keeps piling up inside SDN controller. Nobody takes care of removing the expired flows. And we will see as part of our case studies how we have successfully exploited such kind of issues. So this is a quick video, and to give you a quick reference, how many users, active industry users, are working on NMDA based data stores in their SDN solutions as we speak. And most of us are familiar with many names here. So now we have clear understanding of how NMDA has helped SDN, and we also have clear understanding of there is some semantic gap between 3 different layers. How do we attack this semantic gap? How do we exploit the semantic gap? So as part of that, we propose a fuzzing architecture here. We create a list of services that we are going to fuzz at the moment. This is the input state, and state is important because ultimately at the end we will do a verification of input state, and input state is also the desired state. This is what I want to go into the network. So as part of preparation agent inside SDN Fuzzer, we select different services to be fuzzed. We make REST queries and also we collect REST responses. Based on this REST responses, we decide what data stores are being used. For example, operations with configuration and operational data stores are different. You can put and pull information from configuration data store. However, you cannot do the same with operational data store. So based on the REST responses, we decide what data store it is. When we know what data store we are going to target, what we do is we create random traffic. It's easy to create random traffic in SDN. There are more than 10 tuples that we can play in OpenFlow rules. We create so many OpenFlow rules, and we create network traffic which generate network events. And when we generate network events, what we finally collect is what is the state of the network. Finally, when we have controller state and network state, and also the final configuration that is being reflected in operational data store, as part of output, we collect all these states together. What do we do now? We just validate. Is the intent of the user or application has successfully being put on the network or not? Does the output state abide with what the intended state as part of input in the first place was? If not, we dig into issues. We find where exactly in the information flow this a vulnerability stemming from semantic gap could have caused some issue for this inconsistent network state. So as part of our experiment setup, we are using both the prominent open source SDN controllers, OpenDelight and Open Network Operating System. I should point out that these are also the base SDN controllers for many proprietary vendor-based SDN solutions. As part of our network, we use both a toy network, which is a OVS-based network simulation tool. We also test this out on a close to industry level of network, which is a Science DMZ data center at Arizona State University. So some of the services that we are interested to target or first to see the state of the services during the input and output stages is load balancing. Load balancer, software-based learning switch, topology manager, and flow manager. These are the results. So what do we see here? There are different attacks that we populate here based on different categories and different kind of classes that they belong to. A more exhaustive list of attacks and their explanation is put on the paper, so I would encourage you to find more details if you're interested. However, for the simplicity's sake, we are talking about the results in the sense that where does the attack originate from? If the attack is originating from application or the network, or from the controller itself. We also define the severity of the attack. For example, this is again reflecting the standard CVSS scores. Is it having high impact or low impact? Finally, the status. Have you reported this issue? If you have reported, have they made a responsible disclosure? And also, are the implementation are the solution to the vulnerabilities on hold or not? So let's dig into a couple of case studies here. So case study number 1, we are going to see denial of service attack on SDN controllers. So this is the table where you see as the time went by, we kept on increasing the amount of flow rules that we were installing inside SDN controllers. So again, going back to our initial discussion that nobody takes care of this information which keeps piling inside SDN controllers in an ideal standard setting of NMDA. So what happens is, what happened in our experiments is, we overloaded Open Network Operating System to the extent that it was totally inoperable. We overloaded OpenDelight controller to the extent that it just crashed. And it is a severe issue. We should note this, that in an SDN setting, an SDN controller is a central point of failure. If a central point of failure has crashed, the network is running at no one's mercy. It's a serious issue to be pointed out here. And this attacks were we could generate this kind of attacks or random flows right at the application level, also from the host level by having distributed denial of service kind of attacks. So we made a responsible disclosure of this vulnerability to the concerned organizations. They created a CVA for announcing this kind of vulnerabilities and problems to their partners and their customers. Also, they pointed out that this particular attack in this case study had a high impact on the availability of the network. Since it's a denial of service attack, we understand that. So also it is to be noted that they said that at this moment we are announcing this to our customers, but we are not going to fix this issue just now. And finally, the another case study that we are going to look at into is how to hack security policies. So let's take an example over here. We have applications, controller, and network. The application installs, by default, the A to B communication is denied. Let's say we install a configuration which allows communication between A to B for 30 seconds. And now we do the wait game. How do we wait? Because every switch will have its own counters. Now we are waiting for those timers to expire. What do you expect? We expect that when the timers expire, the flow rule should just disappear. However, just near to the expiry of the timer, if we can create an event from the host which can trigger the controller to reinstall the flow rule inside network switches, what we can force the controller to do is it can take the expired configuration. So if you see, even if the reset was to happen, should have happened for the remaining amount of time, not for 30 seconds. It was just having remaining 1 second to work on the setting. But now the red loop that you see is the hack loop. The communication that in an intended state should have happened only for 30 seconds can now happen for an infinite amount of time. We made a responsible disclosure again to concerned organizations. And again, they identified that it is a security issue. But at this stage, they did not say they will not fix it. we had gathered enough attention for them to work on the design and the discussion. So it is under investigation. It is also worthy enough to note that this particular vulnerability had impact on availability, confidentiality, and integrity of the network. And this is very interesting over here, as we are also proposing some measures to bridge this gap. We have identified the problem, and as part of that, to bridge the problem with denial of service, what we propose is set the percentage of heap utilization. As part of blood ownership, we propose to use metadata. Metadata flows from controller to from services to network and back, and can get updated with who owns this information. Okay, to summarize, what we have done is we have discovered serious design vulnerabilities in the heart of SDN, which is NMDA design. We have used these vulnerabilities and exploited them to cause some serious exploits and attacks, which can be reflected back in any network enterprise setting which is using NMDA. We could compromise the performance of controller. We could create misconfiguration and inconsistencies. We made a responsible disclosure of this and also highlighted the need for redesign. It's not an implementation issue. It is something to do with the core of the SDN itself, which is the design of it. And finally, we also propose some semantic gap, narrowing the semantic gap measures. That's all for this presentation. I can take up the questions. Thank you.
Hi.
Hey.
Adam Bates, University of Illinois. So this has kind of been a fun session because we had two papers that are sort of converging on all of these issues with the way that SDN controllers represent data, right?
Absolutely.
So I don't know if you and Ben had an opportunity to trade notes before the session, or if you were busy preparing your materials while he was presenting. But I'm just so I'm curious. How do you think some of the issues with cross-app poisoning might interact with the sort of the semantic gap inconsistencies that you identify in this work?
Absolutely. We did not get time to talk about the issues that we are facing, but during his presentation, I did make a same note that some sense of missing ownership or the permissions in the earlier presentation, were also leading to the problem that in the inherent data store design, we do not assign ownership. Nobody cares for information, who owns this information, and who should take any actions on them. So yes, in this research, we are also talking about so many other implementation issues that revolve around SDN setting, but not on an implementation specific, for example, not on any particular SDN controller, but a design that is being used by all the SDN controllers as we speak today.
Yeah. It also seems there's a in our paper we were assuming sort of the consistent state of the network, and it looks like there's an entire class of other sort of semantic gap attack attribution issues that are going to exist, being given rise to actual inconsistencies between network state. So cool.
Yes, thank you.
Well, let's actually get more questions.
Yes, just a comment actually. So Goveko from Texas A&M University. So I just checked your URL and for materials, I didn't find that. Can you, tell us what exactly is released here and where, for example, is source code or any data or what kind of available? Because I just checked, it's not there.
Thank you for that question, though. So first things, it is something to do with not to do with the particular implementation. It's something to do with the design itself. It's something to do with the inherent design. To hack this design, we have a couple of applications. We deploy applications at the application level, and we also deploy services at the controller level. So some part of the code is now open source, but not all of it. We will shortly make it available. Yeah. Thank you.
Let's thank our speaker again.